Okay, so yesterday we were talking about this and we looked at this 1 meter long string. This could be like the world's biggest guitar, whatever it is. And when we get this string to vibrate, we have certain wavelengths that will work, that will create a standing wave on this thing. So for this first one, we said that the wavelength of this first wave was what?
2 meters.
2 meters. So lambda 1 is equal to 2 meters. And for the second one, I'm drawing these badly, we said that lambda, so this is lambda 2, was equal to what? Pardon? Length. Yeah, it's equal to the length, so it's equal to 1 meter. And for lambda 3, this is the hardest one for me to draw. Okay. Lambda 3 is equal to what? So yeah, 2/3 of a meter, and we seldom use fractions around here, but today we do. And if we get to this fourth harmonic, what's lambda equal to? Yeah, lambda is equal to, so lambda 4 is equal to 1/2 of a meter. Do you see any kind of trend developing here?
Getting smaller.
Well, the wavelengths are getting smaller. Oh, I'm never going to be able to do this. I did it. It's really sloppy, but we'll take it. So lambda 5 is equal to what? 2/5. Okay. Let's examine something here. Oh, how many of you see a pattern? No, I see bumps. Okay. We could substitute for every place that it says meter, because the length here is 1 meter. We could substitute, and we'll do this, L for length. So this would be 2 times L. Lambda 2 would be L. Lambda 3 would be 2/3 of L. Lambda 4 would be 1/2 of L. Oops, and I forgot to even put my M in there. And lambda 5 would be 2/5 of L. Okay, great. Well, that was exciting, Moser. I'm done now. Well, there is something actually kind of exciting. There's a pattern here. Because we're not going to be doing the sound chapter, I want to kind of do a little bit of this here, because normally we would do more of it there. Really, in every case, the formula, let me pause and shrink. So in every case, lambda equals 2 over n, where n equals the number of antinodes, 2 over n length. So for, I'm going to draw a really crazy harmonic here. Crazy, I told you. I can't even do it. For the 12th harmonic, what's the wavelength? Well, yeah, oops. Yeah, 2 over 12 L, or 1/6 L, a sixth the length of the string. So you can immediately come up with the wavelength for any harmonic of a vibrating string. And what's interesting is actually, especially for the musicians in the crowd, let's clean that up a little bit. These same harmonics exist in vibrating pipes or tubes. So if you have a pipe that's open on both ends and you whack it and you set the column of air within it vibrating, you get these same harmonics. And the same if you blow across it, like with a flute, where you're causing the column of air. If you have a very what I will call primitive style flute, which is just a tube that's open on both ends with a little hole in the top, and you blow across that hole and you set the air inside that tube to vibrating. It's the same harmonic pattern as you would see on a string. So because we're not going to do the sound chapter, you can do any harmonic using that formula. So those are the fundamental frequency and all of the subsequent harmonics, of a vibrating string. Okay, that really actually does wrap up chapter 12. So at this point, I will turn you loose to work. Of course, you're going to have tomorrow to work. Thursday to brush up on, well, I'll give you an option. We'll talk about that once I shut off the video about the schedule for the rest of the week.